All right, so we are still on chapter 1. So we are on 1.2 for section 2.3 because we are in day 3. So chapter 1, section 2, day 3. And we're looking at symmetry of graphs. Symmetry of graphs. And how you prove symmetry, not just by looking at the picture of the graph and stating what it is, but you have to actually prove what it is. So first, we're going to look at x-axis symmetry. So x-axis symmetry, a little quick sketch right here on the side, is if you are symmetric around the x-axis, something like this is x-axis symmetry. To prove that, if you're given the function, the test, to test it algebraically, the test is replace y with negative y. So when you test x-axis symmetry, the x stays the same and you change y. And then after that, you're going to simplify. And then you're going to compare to the original function. Compare to original function. So that's your 3 steps for the test, x-axis symmetry test. So we're going to look at an example. We have y equals x to the 3rd power. And we're testing this algebraically to see if it has x-axis symmetry. So what we're going to do is everywhere there is a y, since we're testing x-axis, we're changing y's. So everywhere there's a y, we're going to put a blank set of parentheses. So there's a y there, blank equals x to the 3rd power. And in the blank, we are going to put a negative y. Blank parentheses, where you're going to fill in your value, are very important. They keep you from making a sign error, which was probably the #1 biggest mistake on this last test, was not having parentheses, plugging something in that was negative, squaring it, and it staying negative. So put blank parentheses there, put the negative inside. Next step is to simplify. So we have on the left, we want to simplify to where the left side is the same, and then we'll compare the right sides. Negative y in parentheses, those parentheses are not doing anything. So negative y equals x to the 3rd power. We want to match the left side. We started with a positive y on the left. That is a negative y on the left. So if we multiply both sides by a -1, it takes care of that negative. So now we have a positive y on the left equals negative x to the 3rd power. So now the left side is the same. Y equals y equals. So now we're going to compare our original function to what we have. We're going to compare these. Y equals x to the 3rd power. Y equals negative x to the 3rd power. That is not the same. Since they are not the same, therefore, so my symbol for therefore is these 3 dots in a triangle, like that. No x-axis symmetry. And that is the answer for does this function have x-axis symmetry? No, it does not. So let's do one more example for x-axis symmetry. This time I'm going to do x minus y squared equals 1. I'm testing this for x-axis symmetry, so I'm going to come over here to the side. I have x minus, there's a y, so I'm going to put a blank set of parentheses. But squared equals 1. In the blank, I'm turning all my y's into negative y's, so I fill in a negative y. Next step is to simplify. Nothing's happening with this x minus, so I'm just going to write that down. X minus. I have parentheses squared, so that's everything in parentheses times itself. So negative y times negative y is positive y squared, right? The negative times negative becomes positive. So y squared equals 1. So then the left side is the same as the left side, so I'm done simplifying. I'm going to compare the original function to the result. These are exactly the same. So that tells me, therefore, it has x-axis symmetry. All right, that is x-axis symmetry.
Why does the negative and the negative sign still have a negative?
Why does the negative and the negative still have a negative? All right, this negative is in parentheses, and it's being squared. So it's negative y times negative y. So let's take this over.
Oh, okay.
Okay.
I see.
Yeah, so we have negative y times negative y, and that's y squared. Okay, so part 2 is then y-axis symmetry. So a quick sketch of what that looks like. It means it's the same on both sides of the y-axis. If you were to take your paper, fold it on the y-axis, you should have the same thing on both sides. That's how you prove it graphically, just by looking at it, but we have to prove it algebraically. So we have the same, the test here, we have a test for that. It's very similar. The test is to replace x with negative x. X with negative x. Simplify and compare. So almost the same as the test for x-axis symmetry, but when you test y-axis symmetry, y stays the same and you change x. So B is our example. We're going to use the same example, y equals x to the third power. But this time, y is staying the same. And so the x is where I put my parentheses, and it's to the third power. And I plug in a negative x. All right, so if we have negative x to the third power, it's negative times negative is positive, times another negative makes it negative again. So an odd power, your negative will stay negative. So y equals negative x to the third power. We've simplified all we need to simplify because the left is y equals, it's y equals. and we compare the right. So we have y equals x to the third power, y equals negative x to the third power. These are not the same. Therefore, no y-axis symmetry. All right. We'll do another example for y-axis symmetry. Y equals negative x squared plus 6. Test that for y-axis symmetry. Testing y-axis, y stays the same. There's a negative sign, and then I get to the x. That's where the parentheses go. The parentheses are squared, plus 6. Then I fill in my negative x in the blank. So then when I simplify, y equals negative. What's in parentheses is what's being squared. So negative times negative makes that positive. So this is x squared plus 6. Since I started with a y equals, and I am now at y equals, I'm finished simplifying. And I'm going to compare the start to the finish. Those look exactly the same. These are the same. Therefore, y-axis symmetry. And then y-axis symmetry has an extra little note that we're going to put on the bottom that really we'll deal more with later, but I'm going to point it out now. Y-axis symmetry means the function is even. Y-axis symmetry means the function is even. So if you prove y-axis symmetry, then you know you have an even function. Because that can be tricky, but we'll talk about more about odd and even functions later. Okay, so now one more part. We have part 3, one more type of symmetry. Part 3 is origin symmetry. I'm going to do 2 little sketches of what this might look like. And it could look like other stuff too. This is just 2. You have that. If you take quadrant 1 and you rotate it around into quadrant 1 and you rotate it around to quadrant 3, that is rotational. It rotates about the origin, and you have origin symmetry. Another one, you could have, I'm going to do this way. This one and this, a rational function. You take quadrant 2, you rotate it around to quadrant 4, and it looks the same in quadrant 2 as it does in quadrant 4. So those are both examples of origin symmetry. So it too has a test. This test is to replace both. X and y with negative x and negative y. And then simplify and compare. All right, so your example for origin symmetry. Y, same example. Y equals x to the third. So the same example we used on the first two. But this time, since this is testing for origin symmetry, we have to test x and y. So y, and I'm going to put a blank, equals x, I'm going to put a blank, because I'm putting blanks for x's and y's, to the third power. So my positive y is now a negative y. My positive x is now a negative x. And then I simplify. On the left, I have a negative y in parentheses. Those parentheses aren't doing anything. So just negative y equals, and then on the right, I have a negative raised to an odd power. So that means it stays negative. And then x to the third power. Remember I said we want what's on the left to match what we started with, and then we will compare what's on the right. We started with a positive y, so we want this to be a positive y. So I'm going to multiply it by negative 1 on the left. If I do it on one side of an equation, I must do it on the other side. So now on the right, I have a positive y, and that equals negative times negative, makes this a positive x to the third. And then I compare my original function with my simplified function. Those are exactly the same. They are both y equals x to the third. Therefore, origin symmetry. And then I also have an extra note about origin symmetry. Origin symmetry means the function is odd. Okay, so your assignment is page 20. Numbers 24 to 33, all of them, and then 63 to 67, odds only. You do not have to do the graphing, so no graphing. You may graph if you want to, it's just not required. So that's your assignment to go with these notes.